Alright, hopefully when you took the quiz you answered that there would be absolutely zero work done. There's also zero change in potential energy. And that's because we're staying at the same point on the land. If you think of this as a mountain, let's say that you go up the mountain a little bit and then down the mountain a little bit and back to the exact same height that you were before. Well, you can say, well, it took effort, it took energy to get up the mountain and then back down. But in terms of potential energy, how much work is done by the field, in that case, no work is being done. There's no change in electric potential energy. And it's completely path independent. We can go down the mountain and then back up. We can go up to the top of the mountain and then back down to the other side. No difference. Nothing happens, okay, in terms of electric potential energy, because we're at the same point on the landscape in terms of the height that something could fall. So that gives us hopefully an understanding of a basic situation. Let's look at a slightly more complex situation. So here we have a much more nuanced view of what electric fields look like and what the electric potentials look like. So I have two positive charges here and another positive charge over here and one negative charge there. And one of the things that you should be able to see is that in order to get, and this is a negative 66, so I've labeled the electric potentials. This is negative 66 right here. This is positive 67 right here, and you can imagine 66 is slightly further away, right? To get to a negative 66, which is pretty deep down, if you think of this as like mountains and valleys, negative would be a pretty deep ditch. I have to get much closer to this negative charge than I do to this positive charge to get positive 66. The question is why? Why would that be the case? Well, the answer, hopefully you can see, is that there's another positive charge nearby. So it's sort of like if you take a bedsheet, and I'm going to use bedsheet analogies quite frequently when talking about electric fields and electric potentials. Let's say you take a bedsheet and you pick it in between two of your fingers and pull it up. And then you pick a point nearby and also pull that up. Well, what that's going to do is it's going to cause the whole landscape in between them and near them to rise up, much more so than if you only plucked the bedsheet and lifted it up at one point. And so these two are kind of mutually building the landscape up around them. The shading that's here, the reds and the blues, are giving us an indication of how tall or how deep the particular area is. So the redder it is, the taller it is. And we can see here that these are on its pretty high sort of mountain peaks. This one is kind of on its own, and this is a ditch kind of by itself. And the white area, where it's not blue or red, gives us right around 0, which you can see here. But you can get these really interesting, strange shapes for equipotential lines, and I can prove it to you. If I take this point right here, that's around 11, right, 10.9, which is exactly what this reads over here. And as I trace along it, you can see that it stays right around 10.9 or 11. So the other thing that I want to draw your attention to is the electric field lines. And you can see that the electric field lines are just as before, typically perpendicular to the equipotential lines, no matter how weird the shape is. And so you can see in this region here, we have this sort of weird curving effect. And that's just because the slope is changing very dramatically in this area, and it's sort of twisting and curving to the effects of the positive charge in the lower right-hand corner and the negative charge in the upper right-hand aspect of the screen. And you can see that there's also a place in between these charges, the sort of positive grouping and the negative, or I'm sorry, the positive grouping in the upper left and the positive grouping in the lower right. We have this space where all the electric field vectors seem to be kind of pointing in towards the middle and sort of chaotic. And what's happening in here is we're getting what's called a saddle point. So you can think of there's being sort of a saddle and everything's going towards the bottom of the saddle. And then it slips off either to the one side or to the other side. As I've said before, there's really no substitute for getting into these simulations, trying things out, playing around with them, seeing what happens, what the results are of those things. Play around with your electric field sensors so you can see, right here we've got basically nothing going on. If I can get to a point. One thing that you'll see though is that I can't get a 0 in here. One of the reasons that I can't get a 0 in here is because I've lifted this up, and so in between them we don't actually get down to 0. We get down to a lowest point, and I found pretty much the lowest point here, because you don't see an arrow pointing to any other particular direction. It's just going to kind of rest there. If I move it a little bit off to the side, right, it tips over this way. If I move it a little bit off to the side this way, it tips over that way. If I move it towards one of the positive groupings, it shifts it down towards the middle again. Okay, so I strongly encourage you to open up this PHET simulation and play around. Right now, you don't need to know a lot of specifics with equations. You just need to get some familiarity with the concepts of electric field, equipotential lines, how they relate to each other, where the electric field lines tell us the steepest way down, and the equipotential lines give us a contour map of the landscape. Understanding these things and understanding how different charge arrangements give rise to different structures, different landscapes, will help you a great deal in the future. So please take the time to do that, and hopefully you'll get a very solid understanding of how this works.